Hello students, in today's lecture we are going to cover uh, exercise part and we will solve exercise problems from 7.1 to 7.7 on the chapter Gravitation. This is disclaimer. Learning objectives. By the end of this lecture you will able to solve questions on gravitational physics by applying concepts of the gravitational force, gravitational potential energy, and orbital mechanics using proper reasoning and calculation. In today's lecture, we will cover NCERT exercise problems on gravitation. There are total 21 questions in this exercise, but we are going to cover only 7 questions, that is from 7.1 to 7.7. So question is, uh, answer the following. There is a 3-part A, B, C. So first A is, you can shield a charge from electrical forces by putting it inside a hollow conductor. Can you shield a body from the gravitational influence of nearby matter by putting it inside a hollow sphere or by some other means? B is, an astronaut inside a small spaceship orbiting around the Earth cannot detect gravity. If the space station orbiting around the Earth has a large size, can he hope to detect gravity? And C is, if you compare the gravitational force on the Earth due to the Sun to that due to the Moon, you would find that the Sun's pull is greater than the Moon's pull. Alright, you can check these yourselves using the data available in the succeeding exercises. However, the tidal effect of the moon's pull is greater than the tidal effect of the sun. And why? So let's see the solution. Now we are going to solve each parts one by one. So A, the answer is no. Gravitational influence of matter on nearby objects cannot be screened by any means. This is because gravitational force, unlike electrical forces, is independent of the nature of the material medium. This means that no matter what material you use, it won't affect the gravitational pull. This is the different from electrical forces, which can be influenced by the medium. Also, it is independent of the status of the other objects. This means that the presence or absence of other objects does not change the gravitational influence. It's a constant force that acts regardless of external conditions. Alright, now second B part. Yes, if the size of space station is large enough, then the astronaut will detect the change in Earth's gravity. Alright, this is because the gravitational force experienced depends on the distance from the Earth's center and the mass distribution around the astronaut. See, tidal effect depends inversely upon the cube of the distance, while gravitational force depends inversely on the square of the distance. So, gravitational force decreases with the square of the distance. This means that as distance increases, the gravitational pull weakens significantly. since the distance between the moon and the earth is smaller than the distance between the sun and the earth. Tidal effect of the moon's pull is greater than the tidal effect of the sun's pull. Alright. 7.2. Choose the correct alternative. Alright. A is acceleration due to gravity increases decreases with increasing altitude. Alright. So here you have to find out the acceleration of the gravity increases or decreases when the altitude increasing. B part, acceleration due to gravity increases or decreases with increasing depth. So assume the earth to be a sphere of uniform density. So again here you have to find out the acceleration due to gravity increases or decreases with increasing depth. Alright. C part, acceleration due to gravity is independent of the mass of the earth or independent of the mass of the body. And D, the formula minus capital M into small m into 1 divided by R2 minus 1 upon R1 is more or less accurate than the formula mg into R2 minus R1 for the difference of potential energy between 2 points, first point R2 and second point R1 distance away from the center of the earth. Alright, so we will solve this question one by one. So first, acceleration due to gravity decreases with increasing altitude. Let's see the reason. Acceleration due to gravity at height h is given by the relation, and that relation is gh is equal to 1 minus 2h divided by re into small g, where re is the radius of the earth. Small g is acceleration due to gravity on the surface of the earth. And it is clear from the given relation that acceleration due to gravity decreases with an increase in height. Alright. B part, acceleration due to gravity decreases with increasing depth. Alright. So acceleration due to gravity at depth d is given by the relation. So the relation is gd is equal to 1 minus d divided by re into g. So it is clear from the given relation that the acceleration due to gravity decreases with increasing increase in depth d. Alright. Now see, the correct answer is mass of the body. So acceleration due to gravity is independent of mass of the body. So acceleration due to gravity of the body of the mass m is given by the relation. So g equal to gm divided by r square, where g is universal gravitational constant, m is the mass of the earth, r is radius of the earth. Hence, it can be inferred that acceleration due to gravity is independent of the mass of the body. Alright. Now, let's focus on D of this exercise. So, answer is more. It means the formula minus m into m divided by into 1 by r2 minus 1 by r1 is more accurate than the formula mg into r2 minus r1. So the gravitational potential energy at 2 points r2 and r1 from the center of the earth is given by the specific equations. And the equation is V of R1 is equal to minus Gm into m divided by R1, and V of R2 is equal to minus Gm into m divided by R2. So the difference in potential energy between these 2 points is V equal to V of R2 minus V of R1. So when we substitute the value of V of R2 minus V of R1, you will be get the answer of V, that is equal to minus Gmm into 1 upon R2 minus 1 upon R1. Alright. Hence the formula is more accurate than the formula mg into R2 minus R1. Now 7.3. Suppose there existed a planet that went around the sun twice as the fast as the earth. What would be its orbital size as compared to the earth? Alright, so let's see the solution. Now first we need to define some terms. Re is equal to Earth's orbital radius. Rp, planet's orbital radius. Te is Earth's orbital period, that is equal to 1 year. And Tp is planet's orbital period, which is equal to 1 by 2 year, since it goes twice as fast. Since the planet goes around the sun twice as fast as Earth, this means its orbital period is half of the Earth's orbital period. So mathematically, we express this relationship, that is Tp is equal to 1 by 2 Te is equal to 1 by 2 year. Alright. So now according to Kepler's third law, which states that the ratio of the cube of the radius of a planet's orbit r cube to the square of its orbital period t square is constant for all planets orbiting the sun. Therefore, Re cube divided by Te square is equal to Rp cube divided by Tp square. So substituting the known values, Re cube divided by 1 square is equal to Rp cube divided by 1 by 2 whole square, 1 by 2 square. Alright. Now solving for Rp. So Re cube divided by 1 is equal to Rp cube divided by 1 by 4. So Re cube is equal to 4 times of Rp cube. So Rp cube is equal to Re cube divided by 4. So Rp is equal to Re into cube root of 1 by 4. So solving these calculations, you will be get Rp. So let's continue with solution. So we use the formula Rp is equal to Ra into cube root of 1 by 4. So which is approximately equal to 0.63 into Re. Hence the orbital radius of the planet will be 0.63 times smaller than that of the Earth. This means we can say mathematically Rp is equal to approximately 0.63 Re. Io, one of the satellites of Jupiter, has an orbital period of 1.769 days, and the radius of the orbit is 4.22 into 10 raised to the power 8 meter. So that the mass of the Jupiter is about 1000th that of the Sun. Let's see the solution. So the first thing to note that is I note one of the Jupiter satellites revolving around the Jupiter. So orbital radius of IO is equal to 4.22 into 10 raised to the power 8 meter. And orbital period of IO is 1.769 days. So it will be in second 1.769 into 24 into 60 into 60. So it will be 152,841.6 second. All right. Now, using the Kepler's third law, which relates the square of the orbital period to the cube of the orbit's radius. The formula T square IO is equal to 4 pi square R cube IO divided by G mg. So where mg is mass of the Jupiter, TIO is the orbital period of the satellite. Mass of the Jupiter can be written as mj equal to 4 pi square R cube divided by G T square. Alright. Now, let's start by considering the Earth's orbital period, which is 365.25 days. So in second, it will be 365.25 into 24 into 60 into 60 second. So performing the calculation, you will be get 31557600 second. Orbital radius of the Earth, which is 1 astronomical unit. This is approximately equal to 1.496 into 10 raised to the power 11 meter. So mass of the sun can be written using Kepler's third law. So ms is equal to 4 pi square Re cube divided by gt square. All right. Now, let's start by considering the formula for the mass of the sun ms, which is equal to 4 pi square Re cube divided by gt square, and the mass of the Jupiter, and that is 4 pi square R cube divided by G T square. So performing the calculation, ms by mj, you will be get ms by mj is equal to Re cube divided by IO cube into T square IO and TE square. All right. 4 pi square cancel out, G cancel out. The remaining term is this one. So substitute the values. Re equal to 1.496 into 10 raised to the power 11 meter. RIO is equal to 4.22 into 10 raised to the power 8 meter. And TIO is equal to 152,841.6 second. And TE is equal to 31557600 seconds. Alright. So expression involves raising the ratios of the powers, which emphasizes the sensitivity of the mass to change in radius and period. Alright, these calculations will shows us that Jupiter's mass is about 1000 that of the sun. So solving this calculation, you will be get the ms by mg. Now, solving for the ratio of ms and mj, you will be get ms by mj is equal to 1045.04. It means ms upon mj approximately 1000. It means ms approx 1000 into mj. Hence, it can be inferred that the mass of the Jupiter is about 1000 of the thousands that of the sun. Let us assume that our galaxy consists of 2.5 into 10 raised to the 11 stars, each of one solar mass. How long will a star at a distance of 50,000 leap year from a galactic center take to complete one revolution? Let's see the solution. Mass of the galaxy Milky Way m is equal to 2.5 into 10 raised to the 11 solar mass. And solar mass of the sun is equal to 2.0 into 10 raised to the power 30 kg. So multiplying, you will be get 2.5 into 10 raised to power 11 into 2 into 10 raised to power 30. Solving this, you will be get 5 into 10 raised to power 41 kilograms. All right. So first, we need to know the diameter of the Milky Way, which is given as 10 raised to the power 5 light years. Uh, Radius of the Milky Way R is equal to 5 into 10 raised to the power 4 light years. We know 1 light years is equal to 9.46 into 10 raised to the power 5 meter. So R equal to 5 into 10 raised to the power 4 into 9.46 into 10 raised to the power 15. So R equal to, solving this, you will be get 4.73 into 10 raised to the power 20 meter. All right. So to solve this, we will use Kepler's third law, which relates the time period of an orbiting body to its distance from the center of mass. The formula T square equal to 4 pi square R cube divided by Gm. So T is equal to 4 pi square R cube divided by Gm whole power 1 by 2. So substituting the values, you will be get T is equal to 4 into 3.14 whole square into 4.73 cube into 10 raised to the power 60 and divided by 6.67 into 10 raised to the power minus 11 into 5 into 10 raised to the power 41 whole power 1 by 2. So solving this, you will be get T. Now let's solve for that period T, which is the time it takes for the star to complete one revolution. So solving this, you will be get T. So T is equal to 1.12 into 10 raised to the power 16 seconds. Now converting the time from second to years. So 365 into 24 into 60 into 60. So you will be get 1 second is equal to 1 upon 365 into 24 into 60 into 60 years. So performing the calculation, you will be get the relation between second and years. So T equal to 3.55 into 10 raised to the power 8 years. All right. Choose the correct alternative. A. If the zero of potential energy is at infinity, the total energy of an orbiting satellite is negative of its kinetic potential energy. B. The energy required to launch an orbiting satellite out of the Earth's gravitational influence is more or less than the energy required to project a stationary object at the same height as the satellite out of the Earth's influence. So let's see the solution. A. For part A, we need to understand the relationship between total energy and kinetic or potential energy for an orbiting satellite. So total mechanical energy of a satellite is the sum of its kinetic energy, always positive, and potential energy may be negative. So at infinity, the gravitational potential energy of satellite is zero. This is an important concept because it sets the reference point for potential energy in gravitational fields. Since the Earth satellite system is bound system, the total energy of the satellite is negative. This indicates that the satellite is gravitationally bound to Earth, unable to escape without additional energy. Thus, the total energy of an orbiting satellite is infinity is equal to the negative of its kinetic energy. This highlights the balance between the kinetic and potential energy in maintaining the satellite's orbit. Next, B part. A satellite requires relatively less energy to escape Earth's gravitational field This is because of the kinetic energy it already possesses from its orbital motion, which plays a significant role in the energy dynamics. Orbiting satellites already have kinetic energy due to their motion. This existing energy is crucial because it reduces the additional energy needed for the satellite to escape Earth's gravity. This existing kinetic energy reduces the additional energy needed for escape. All right. In contrast, the stationary objects at the same height require more total energy to escape since they start with zero kinetic energy. This means they need to gain all the necessary energy from an external source to overcome Earth's gravitational pull. Does the escape speed of the body from the Earth depend on A. The mass of the body, B. The location from where it is projected, C. The direction of projection, and D. The height of the location from where the body is launched? Let's see the solution. Uh, let's begin by understanding the formula for escape velocity. The escape velocity of body from Earth is determined by a specific relation. That is V escape is equal to under root 2 gr. G is acceleration due to gravity, R is the radius of the Earth, and now we will solve A. So it is clear from the above expression the escape velocity V escape is independent of the mass of the body and the direction of its projection. Alright, now B. So escape velocity of the body from the Earth is given by the relation, that is V escape is equal to under root 2 gr. So escape speed depends on the height from the Earth center where the object is launched. So, but not on the geographical coordinates of the launch site. So, C part. As escape velocity of body from the Earth is given by the relation. So, V escape is equal to under root 2 gr. So, the escape speed is scalar quantity, meaning it has only magnitude and no direction. As long as the body reaches the required speed, it will escape regardless of the initial direction of projection. Now, D. So, as escape velocity of the body from Earth is given by the relation, that is V escape is equal to under root 2 gr. So the greater the distance r from the Earth center, the lower the escape velocity needed, as gravitational pull weakens at the higher altitudes. This is because the gravitational pull weakens at higher altitudes, making it easier to escape. So escape velocity depends on height h. Thank you for your attention.